enjoys fiction. And today she's going to tell us what insights we can learn from use cosmology about dark matter.
Great. Thank you very much for having me here, and I'm really excited to be here to tell you about some new developments that have happened from a cosmological perspective in probing dark matter physics. So the big idea here that I want you to take away is that we can actually use cosmological astrophysical observations, these large-scale observations, to say something about the microscopic nature of dark matter. So to do that, let me first go into sort of the standard story of dark matter in cosmology, namely the lambda-CDM paradigm, and how we normally view dark matter in a particle physics context historically. And then I'll talk about tests in cosmology, specifically if dark matter can have some scattering with the standard model, and show you the ability for specifically the cosmic microwave background to tell us something about the particle nature of dark matter. And then I'm going to break a little bit from the title of my talk and talk about astrophysics as well, and a completely separate line of research that I've been getting into recently that has to do with gravitational waves and what we can learn from that. And then I'll talk about just some future prospects of where this field is going. So to begin with, let's talk about the standard story of dark matter. Here is the depiction of the history of our universe. So time flows from the Big Bang forward to today. I'll usually talk about the redshift instead of time, the cosmological redshift, and this is just saying that as the universe expands, it's going to stretch out light, and the longer it takes light to get to us, the more it gets redshifted. So this is a proxy for time, and redshift of 0 is today. So in the early universe, the plasma was very hot and very dense, and very uniformly distributed. So we had photons, we had matter, and at this point called Big Bang nucleosynthesis is when we get the creation of our first light elements. So mostly hydrogen, so mostly protons, a little bit of helium, and a little bit of the heavier elements as well. And so at this point in time, everything is hot enough such that the universe is ionized. And so the photons are just scattering, Compton scattering with all the ionized particles in the universe. And it's not until this process called recombination, when neutral hydrogen is able to form, that the radiation is allowed to essentially free stream from this era at recombination to be observed by us today. And this is the cosmic microwave background of radiation. So this is essentially the first view of our cosmological history that we get directly. So after this happens, the universe is mostly neutral hydrogen, and we enter this period called the Dark Ages. There's not a lot observationally that we can hope to probe, and it's not until a little bit later on when we reach this period called cosmic dawn that we can hope to see a new observation at a new window in our universe's history. So cosmic dawn corresponds to the formation of the first stars. Okay, so the universe is mostly neutral, and then the first stars turn on, and they start emitting a lot of radiation. This then goes and reionizes the universe. Okay, and so we have a reionized universe today, and we can go out and look at, take telescopes and look at the distribution of today's galaxies, to say something about our formation history. So the periods of time that I'm going to focus on mostly is the cosmic microwave background and galaxy observations today. These have the highest quality data and the most direct data that we have about the content of what's going on in the early universe. And I'll come back a little bit later and talk about this era of cosmic dawn in a different context, okay? So, so it's these two eras that I will be focused on. So just as an overview, what are the main properties of dark matter that we're concerned with in the context of cosmology? So in the standard lambda-CDM scenario, Dark matter is matter, but it has to be distinct from baryons. And cosmology has this, what I consider a little bit an unfortunate convention where they call baryons anything that is non-relativistic matter. So this includes electrons, protons, helium. So these are the baryons, and I'll just use this definition from now on. So it has to be distinct from baryons. It has to be cold, collisionless, and it's much more abundant than baryons. And we know this from this map of the cosmic microwave background radiation that we have from the Planck telescope. Okay. So how does this picture sort of fit in of dark matter to give us this map? And a good way of thinking about it is that if you have a little bit more dark matter, for instance, in some location, and a little bit more dark matter here, what they're going to do is create potential wells for other matter to fall into. So if we have our baryons here in purple, they will see these potential wells and want to infall. Of course, there's radiation that's still running about, and so this radiation will cause pressure and will want to drag these baryons back out. Okay? So we can have this scenario at different scales, at different separations of these potentials, and what we end up having is this simple harmonic oscillator story at different frequencies, different wavelengths, and this is just the Fourier space description of what's happening in the early universe. And what the Cmb does is it gives us a snapshot at a particular time, at the time of recombination, of this oscillation process. Okay. So these potential wells, of course, are very small in the early universe. They're just tiny perturbations. Once again, everything is very smooth, very uniform. But these potential wells will eventually continue to grow, just gravitationally attracting more and more matter. And these are essentially the seeds of the galaxies that we have today. So we have dark matter halos that form the potential wells for galaxies to form and exist at present day. Okay, so this is the story from the early universe. But like I said, we call it dark matter because we need it to act as non-relativistic matter. So if we're going to take seriously this idea that it is indeed matter, then it has some properties, right? It's a particle, it's going to have some mass. Maybe it's not a single particle, there's going to be some composition of dark matter that's maybe multiple particles, and it's expected to have some interactions. So what interactions are those? Are there any new forces that we don't encounter in the standard model? So to answer this question, there's been a long-standing paradigm, and it's called the weakly interacting massive particle paradigm, the WIMP. And this story fits into particle physics, it fits into cosmology very nicely, and it's spearheaded a lot of different searches. So from the particles perspective, there are various channels that we can go and search for dark matter interacting with the standard model of particle physics. So here's a diagram in which I have two standard model particles, two dark matter particles, and depending on how I read this pseudo Feynman diagram will tell us a different interaction channel. So for instance, if I read time top to bottom, this is a production channel where two standard model particles come in and two dark matter particles come out. So you can imagine this being this dark matter being produced in collider experiments like the LHC. If you go the reverse direction, this is annihilation. So two dark matter particles are indirectly detected via detecting their annihilation products that we can't even see. But the aspect that I'm going to focus more on is this concept of scattering. So we have direct detection experiments that go and search for dark matter elastically scattering on standard model particles. So the idea behind direct detection is this. So here we are in our Milky Way traveling at 220 kilometers per second. So in our frame it looks like there's this WIMP wind of dark matter that's coming through the Earth. And so experimentalists have built very large detectors, placed them deep underground, and are searching for this rare interaction between dark matter and some target nucleus. And the idea is that these experiments can then read out that nuclear recoil, that energy that was imparted by the dark matter. Okay. So how often you expect this to happen depends on a couple of factors. One, it depends on the astrophysics. What is the local dark matter density? What is its velocity distribution? It depends on particle physics factors like what is the dark matter mass? What is the actual interaction cross-section with the standard model? And it depends on the parameters of the experiment. So you have the target nucleus, you have that will be more or less sensitive to different types of interactions. And you also have to consider the detector threshold. So these dark matter particles only have so much energy. And it turns out that the state-of-the-art detectors looking for nuclear recoil have thresholds at about 1 to 100 keV. And this translates to them being sensitive to masses, dark matter masses that are above a few GeV. Okay. So there is a way to characterize the interaction between dark matter and a target nucleus or a nucleon. And this is in the context of a non-relativistic effective field theory. So the idea here is this: we can take a Lagrangian, some effective Lagrangian, and write down the various bilinears that we can construct with, spin 0, spin 1/2, spin 1 dark matter, and sandwich it together with a bilinear for the nucleon. Okay, and the nice thing about this is that when you take this Lagrangian and you reduce it to a non-relativistic process, then the overall interaction becomes dependent only on a few low energy observables. So it depends on the dark matter and the nucleon spin. Sure, that's fine. It depends on the amount of momentum transferred in the scattering process. And it depends on the relative velocity of the particles that are scattering. Okay. So we can take this and say that the overall operator, the overall interaction between the dark matter nucleon state that's incoming and the dark matter nucleon state that's outgoing depends on powers of this relative velocity. It depends on this on powers of the momentum transfer. Okay. So for a very simple example, the canonical example is spin-independent scattering, which has no velocity dependence. The Lagrangian is a very simple Lagrangian, looks like chi bar chi, in bar in, and this corresponds to this operator that's just unity. So there's no dependence on the relative velocity, no dependence on the momentum transfer. Okay. So this is often what experiments will cast their limits as. They will look at the spin-independent process and draw exclusions. So here is the dark matter nucleon cross-section in centimeters squared versus the dark matter mass in GeV. And these are the state-of-the-art limits for spin-independent scattering. There are plenty more lines in these shaded excluded regions, but I'm just showing sort of the outline of what's the state-of-the-art in the field. Okay. So as you can see, there's the sensitivity of these experiments is very, very good. They are getting better and they're improving as each generation of experiments comes along. However, there are a few caveats, right? So there's this mass threshold that I was talking about, where these experiments can't really probe anything below a GeV. Also, these experiments tend to, just show the lower end of their plot. So these are actually not upper limits in a strict sense. If you imagine having a very, very high cross-section between dark matter and normal matter, then you have this this concern that the dark matter has to traverse the atmosphere, has to traverse the crust of the Earth to actually get to the experiment in the first place. And if the interaction cross-section is too high, then you're not going to make it. The dark matter is not going to make it down there. So there's a direct detection ceiling where the sensitivity of these experiments just cut off. Okay. This is traditionally not looked at or considered because we were looking for a weakly interacting massive particle, right? It shouldn't have such a large cross-section that we would have to be worried about this. But on the other hand, we haven't seen anything. From direct detection experiments, there's no hint of supersymmetry from the LHC. So, it behooves us as a community to really think about other possibilities for dark matter, to relax a lot of our assumptions that we had and start thinking out of the box in terms of where else dark matter could be. So this is, so getting below this mass threshold has drawn a lot of attention, and this detection ceiling is something that that's very relevant for cosmological observations. So we can search for the same physics with cosmology, and we're going to be able to probe very large dark matter nucleon cross sections with this. Okay. Once again, this isn't the standard story. On the other hand, we haven't detected dark matter in its standard form. So
wouldn't the detection ceilings be mostly covered by the collider stuff?
So that's a good point. So if you have a particular model, then the LHC can come in and say, you know, Higgs-mediated dark matter interactions are going to be ruled out at a certain level. On the other hand, you have to pick a model, right? You have to make this connection between the low energy physics that is probed by direct detection and is going to be probed by the Cmb, for instance. And you have to make that connection between that and some relativistic theory that's going to be relevant for the LHC.
Well, I'm not, the LHC would be not separated to something more like a lab, a bar.
Oh yeah,
and all
so,
of
so
those
for
things,
any
you know,
collider.
for the low energy hadron, the low energy fixed
Yeah.
targets, and those would probe huge cross sections.
Yeah, so I haven't seen any analysis of it. Once again, we haven't really been looking for this. But the signatures that you would expect should be fairly different if you were, you know, it no longer becomes a missing momentum issue. It no longer becomes something like this. It becomes that this dark matter, if you're able to produce it, is able to very strongly interact with your detector. And are you looking for those observables? Are you analyzing your data with that in mind?
I would
Also,
guess that the old
you
stuff
need
would be-
probably both, like electron couplings as well as these photon couplings for
Yeah, for
getting
like-
into those signatures. Like, for example, Bobar or beam dump or
Yeah,
stuff
I would
like
discuss
that.
like KTEV, for example.
Yeah, but here, for example, you can have just a dark matter and a photon. That's it, nothing else.
But the thing that does exist is a lot of recasts of the fact that satellites aren't broken yet for how much dark matter scattering would have screwed with their electronics. I'm trying to remember when these got done. These were done a while ago.
I mean,
The Earth orbits, for example.
This depends on the
That's
level
even more.
of interaction that you're considering, and I'll discuss some other situations where
Okay,
people
right.
have taken.
I think your
experiments
point is well
from-
taken, that a detection ceiling is a very important thing for these
Mm-hmm.
experiments, but it wouldn't surprise me if the very old experiments over the last 100 years really would kill all of that, but I'm happy to be wrong.
It's
It'd
actually
certainly be
also,
really hard to do that on TEV.
Yeah, you wouldn't do this at TV, it's just.
all
yeah.
The ceilings there at TEV still.
Yeah, so.
Yeah, that's right.
all
Yes,
the
please.
dark matter, detectors, what they go through before they go underground, they go through tests in the lab, surface labs.
Yeah, absolutely.
They have actually, they set the best limit on the detection ceiling on the
Yeah.
strongly interacting massive particles.
And I'll show that in just a bit, yeah. But it's sort of, there may be data that excludes it. For instance, I'm gonna show data that excludes it cosmologically. So just because it's there, nobody has done it, nobody has worked on it, and it's something that that I would like to claim from a cosmological perspective, right? We thought, it must be a WIMP, right? Because that's what gives us the right relic abundance in cosmology, and we have to assume that it's basically collisionless, and I'm going to show you that the Cmb doesn't actually tell us that at all.
Come on, that's not, it's just the simplest assumption, right? If
So,
you got lots of murderers, you start with assuming a serial killer, right? It's much easier to solve.
so in terms of, okay, so that's good. This is going to lead me to
Sorry,
now
I
looking
didn't
for
mean
this
that.
documentary.
That was really morbid now.
I watch too many crime shows, what do you want?
Netflix is spoiling it. But
I like
yes.
smart people catching bad guys in under an hour, that's good.
So we can do these tests in cosmology. We can look for the same physics that's done in direct detection. And the main idea behind cosmological observables is this, and it's the idea of small-scale suppression. So that's what you're looking for when you're looking for this effect and similar effects in cosmology. So the idea here is that we have our dark matter potential wells, right? But now we actually have to put particles in them. And if a baryon is going to interact with one of these dark matter particles, then it can kick it out of its own potential well, right? But this is happening presumably quite a bit before recombination occurs. And you can completely destroy very weakly gravitationally bound structures that don't have a lot of dark matter in them. And so you completely suppress structure at various scales. And the smaller the scale it is, the more you suppress it. So you can look for this effect in the CMB. Of course, this also has consequences for galaxy formation, right? So if you destroy the smallest scales, right, these small dark matter gravitational wells, then that's going to have a consequence for the size of the halos, dark matter halos, that it will eventually be able to form today. So, so very small galaxies might not form. So here I'm showing you a large in-body simulation that is under the context of just normal lambda CDM cosmology. So you see here a larger galaxy and a whole bunch of small sub-halos of dark matter, right? So there's a lot of structure here. There are a lot of dots. There are a lot of very small objects that form around this. And this is showing what happens when you just put in a very, very generic small-scale suppression that you would get from an interaction like this. And you can see that all these small halos have disappeared, right? You still have the big main one, but now everything else smaller than than a certain size have vanished. Okay.
So this was the typical type of results that told us that we should stop looking for relativistic dark matter, like
Yes.
light gravitinos and that kind of stuff.
So this is the kind of effect that's telling you limits on, say, warm dark matter. Yes, and it rules out hot dark matter. Yeah. So so let's start with the Cmb tests. This is the latest publicly available Planck data from 2015. And these are the temperature and polarization and isotropy maps, and so you're seeing small fluctuations that are on the order of 10 to the -5 for temperature that are fluctuations of the photon temperature across the very steady 2.7 Kelvin background that we observe, right? So they're essentially all at the same temperature except for these small fluctuations. And so it's easier to recast these maps in terms of a power spectrum. And so you decompose this map in terms of spherical harmonics. So you have a multipole L here, which corresponds to smaller angular scales on the sky. Okay, and these are this is the power spectrum for temperature and for polarization, and these are the data points from Planck. So we can ask now what happens when I put in this additional physics that direct detection searches for. So here I'm showing the power spectrum that we got from just lambda CDM, best fit cosmology. And this is what happens when I introduce a very high amount of interaction, right? This is well ruled out, right? Because the error bars on the Planck data points are very small in certain regions, but this is for effect. So here you can see a little bit enhancement of the first peak. You also get this effect where your peaks shift. But the main effect that you get, that you're actually searching for that's going to constrain a type of model is this small scale suppression that you get out here. So once again, higher multipoles mean smaller scales, and you get progressively more and more suppression as you get to higher multipoles. Okay? So I don't get to choose my experimental target. The universe has done that for me. So the baryons that I'm considering are going to be hydrogen and helium nuclei. Okay, and so I have to assume some sort of interaction, specific type of interaction between dark matter and these nuclei in the universe. So what is my particle physics input? And so this is where I'll harken back to the non-relativistic effective field theory from direct detection and just use this formalism with these various observables, with these different models, with different alpha and beta. I can write down a cross-section that just looks like some constant times the relative velocity to some power. And these powers depend on the particular model at hand, okay? So this is the dark matter response function, if you're familiar with this language from direct detection, and this is the nuclear response function. Mostly because, so this is coming from helium needing a form factor, because there's motion inside of helium with the nucleons. So this is not quite the cross-section, this is the momentum transfer cross-section. So what cosmology really wants to see is momentum transfer. So if you have very far forward scattering where you have a nucleon and you have dark matter particle and they pass through one another, that's not going to do anything cosmologically. So you need, the equations demand that you weight this out, so you prefer backward scattering and you weight out forward scattering. So this is all to say that the CMB is very sensitive, not just to the cross-section, this momentum transfer cross-section, but also just to the overall rate of momentum transfer, okay? So the rate of momentum transfer depends on the scale factor of the universe. It depends on the number of targets that you have, so the baryon number density. It depends on this, this constant part of the cross-section, some mass terms, and the thermal velocity of the particles that are scattering. So it depends on the temperature of the dark matter, the temperature of the baryons. And so this is the quantity that the CMB can actually say something about and constrain. Okay. So here I'm showing the rate of momentum transfer over the expansion rate of the universe as a function of the redshift. So over here at redshift of 10 to the 3 is about when recombination occurs, and 10 to the 6 is the highest redshift that Planck is essentially sensitive to. And at this line, at 1, if you are above this line, then you have an efficient amount of scattering, and if you're below this line, then the expansion of the universe wins, and you don't get that much scattering, okay? So we can now, let me simplify things and just say the momentum transfer cross-section looks like some constant times the relative velocity to some power. So I can choose different powers, so I can consider v to the 4, v squared, something that's independent of velocity, and then start looking at the negative powers as well. So over here, there is a lot of momentum transfer that's happening. So for these particular models, you have a lot of scattering at early times and less scattering at late times. So for these more traditional EFT models where you have some contact operator, you have non-negative powers of velocity, this corresponds to early time scattering. And it's, you have to go all the way down to v to the -4 to actually get the opposite effect, where there's less scattering at early times and more scattering at late times. Okay, so these inverse powers correspond to early being less important and late having a larger effect. Okay, so these models here, this early time scattering is a little bit easier to deal with, so let me go over this first. So you have early time scattering of a dark matter and baryon, and you assume that maybe there's some heavy mediator that's mediating this interaction. That's fine, and we can do the analysis, fit all of Planck's, the typical cosmological parameters, as well as these new parameters to model the dark matter mass and the cross-section with nuclei. And we can do this for all the various different models. So here I'll just pick v to the 0, v2, v to the 4, that correspond to particular models that I showed before for the EFT. And everything above this line for a specific model is excluded by Planck. So note that we go to very low masses, much below what is accessible with direct detection, and we're probing very high cross sections, right? Near nuclear scale for some of these. And all these cross sections, these have various velocity dependencies. Here I'm just evaluating everything at a direct detection sort of velocity of 228 kilometers per second. So this is what comes out of this analysis for the CMB. Right. Of course, now there's the other part of the story, looking at today's galaxies and the formation of galaxies. And here is at the limit of the CMB. Here is the matter power spectrum that you would expect from this. So the matter power spectrum is just telling you how much matter is there in the universe at different scales, right? So this scale is an inverse megaparsec, and you can see that this solid black line is what you would get from just normal lambda CDM. So there's a good amount of power that's at smaller and smaller scales, and these models here, depending on the velocity dependence, depending on the mass, will start suppressing power at some scale. And so this is a log plot. So this is a lot of suppression here, and you see these oscillation effects because you are so tightly coupling dark matter to baryons that the dark matter actually starts experiencing some acoustic oscillations. So this is what you see here in the matter power spectrum. So now we can say, okay, we can look at this matter power spectrum and say, well, we need some amount of structure. And we know we need some amount of structure because we see very small structures. So for instance, if we look at the Milky Way satellites, this is the Milky Way and this is the Milky Way halo. And we see all these tiny satellites of the Milky Way, all right? So in orange are the classic dwarf galaxies that we have observed for a while. And in blue are dwarf galaxies that have been identified by the Sloan Digital Sky Survey. And just by their sheer existence means that we can't have so much interaction that we suppress power such that these don't form, because we see them, we need them to form. So if we just look at the case of spin-independent scattering, velocity-independent scattering, here is my exclusion from Planck. Once again, dark matter nuclear cross-section against dark matter mass. And then if we go ahead and
Is
do...
the presumption that these things they had to have been formed in the beginning and they're still here as opposed to being created by some other mechanism?
Yes, this is assuming sort of the closest thing that you could think of to the WIMP scenario. That they were,
sorry. The presence of the dwarf galaxies exist.
Sorry. Yes.
Fine. Is the presumption here that they were created in the early universe and they're still here,
Yeah.
rather than created by some other mechanism?
Yes, so we assume that galaxy formation is done in a hierarchy.
So-
Sorry.
How good is that assumption?
So they all have very old stellar ages, so they're formed at high redshift.
All right, so we can look at these things and we
Yep.
see that they're very
Yes.
old.
Yeah, none of them have ages that indicate that they're recently formed.
That's useful. Okay.
Yes.
I love having astronomy knowledgeable folks around. Okay, good.
So we can then say how are we going to exclude dark matter interactions in this parameter space, and this is what we get. So we get an order of, a few orders of magnitude better constraints for this particular model by saying that we need to have the Milky Way satellites. We can't have depleted power at these scales such that we don't expect to see them.
So the mediator mass does not matter that much. Right?
So this is assuming like a spin-independent scattering. You have a heavy mediator. So this situation will change depending on how on what type of interaction you're assuming. So this is some work that we've done that will hopefully be out soon. Just for the velocity spin-independent scattering case, we're doing the other cases as well. And so this won't be the story for all the different types of interactions. So it's still important to do things with the CMB, to search for these type of interactions with the CMB. More specifically, the CMB would actually tell us if some interaction were there or if there was some evidence of non-lambda CDM cosmology that we could actually fit to that data, right? It's not just an exclusion bound. At the moment, in the way that we're considering this is an exclusion. This is not being able to fit to a particular type of model at this point. Just because the CMB is much higher quality data, we understand it a lot better. Okay. So to give you a sense of where direct detection falls, here are the direct detection bounds with their ceilings, and you can see that there's this high ceiling from a crest surface line. So it's able to probe much higher cross sections. And so at higher masses, you can see this little gap here. At higher cross sections, other people have taken data from other experiments, like balloon experiments that have flown, and are able to cut into this parameter space over here based on not seeing odd things in that data. However, for the most part, you can't really access anything at dark matter masses that are lower. Because once again, there's only so much kinetic energy these dark matter particles have in our local halo, and you have to see an effect in the detector. So for the most part, everything is confined to be about above a GeV, and that's where we can place most of the constraints with this type of direct detection type search. So this is the story for the models that kind of fit the description of the EFT that I was talking about. We can also think about if you have dark matter that is able to scatter with baryons through some light mediator. So here I'm just going to assume that the mediator mass is much, much less than the typical amount of momentum transfer. And this is so I can write the momentum transfer as some, the cross-section, the momentum transfer cross-section is some power of velocity where this power now is negative. So if I had n equals -2, this would correspond to an electric or magnetic dipole moment interaction. If it's n equals -4, this is something that looks like a Coulomb interaction. All right. So once again, remember that we're interested in the rate of momentum transfer for the CMB. And we expect small cross-sections at early times and large cross-sections at late times. But as the universe cools, this velocity, this thermal velocity, is just going to drop as the temperatures of the dark matter and the baryons drop. But it's not like that this cross-section blows up. There's still an overall motion of the baryons with respect to the dark matter's frame. So there's some motion here that's going to cut this off from going to infinity as v goes to 0. This actually introduces an interesting concern that's very technical, so I'm not going to get into it too much. But it's basically, you're comparing what the bulk relative velocity is between these two fluids, so their overall motion as an entire fluid in the early universe, versus the thermal dispersion that you associate the temperatures of these fluids with. So these large bulk velocities lead to a lot of problems for cosmological computations. And just to give you an idea, these are the equations that I can write down for this simple case. For my temperature evolution of my dark matter and my baryons, and this is their motion, the evolution of their motion. And this is what I get when I have to deal with this nonlinear effect that I get. So this is a mess, and you have these confluent hypergeometric functions you have to deal with now, and you just have to treat this in a certain way that makes the calculation feasible and tractable. And so this is what I did to formulate some new method of handling these messy equations. So let me show you the result that I get for specifically n equals -4. So here is the cross-section in centimeters squared against the dark matter mass once again, and using my new treatment, this is the limit that I find. Okay. Had I neglected all that awful math that I showed you from before, these hypergeometric functions, and just did things very naively, this is the limit that I would have achieved. So I would have overestimated my limit by over an order of magnitude. So including this effect is very, very important so that you're not overestimating things. So I focus on n equals -4 for a very particular reason. And it's because it relates to this experiment called EDGES and something that they have observed. So this is the experiment to detect the global epoch of reionization signature. And what they're doing is they take a dipole antenna, this table out in the middle of the Australian desert, and what they're doing is looking for CMB photons at a certain frequency. These CMB photons have to pass through neutral clouds of hydrogen as they come to us. And so occasionally one of those photons will be absorbed by the hydrogen and excite the 21 centimeter hyperfine transition, right? So you're looking for a deficit of photons in a certain period, around this period that I mentioned before of cosmic dawn, and you're searching for a deficit in this frequency range. Of course, things are redshifted, so they're not going to be at exactly the 21 centimeter frequency, but it will be at some shifted frequency range. So this is what they see. So this is the absorption that they see. They see a deficit of photons. The problem is, this is the most, in the most optimistic case, the most amount of absorption that you should expect from lambda CDM. So there's a 3.8 sigma discrepancy between what this experiment observes and what could possibly be expected from the standard lambda CDM scenario. So at the time that this paper was released in February of last year, there was an accompanying theory paper that said, a V to the -4 scattering between dark matter and baryons could cool the gas, the neutral hydrogen, the baryons, at these late times at redshift of about 17, and allow the hydrogen gas to absorb more Cmb photons, and this you would get a larger absorption depth. Now there are a lot of questions and concerns about the actual observation and the interpretation of it, but let's just take it at face value. So now we have to ask, okay, the amount of scattering that you need to achieve this level of absorption, is that consistent with the CMB? And the answer is yes, sure. So this is the cross-section that you need to explain the absorption seen by edges. However, I specifically wrote dark matter hydrogen cross-section. So in the early universe, everything is ionized, so it doesn't matter if I'm talking about dark matter that can interact with a proton, or dark matter that can interact with a proton with an electron. But we're talking about a V to the -4 interaction. And so if this is a Coulomb interaction, and if we're going to just say a very simple scenario, it's a very simple particle scenario, that maybe it is a Coulomb interaction. Maybe it is the actual photon that mediates this. Then it needs to scatter on ions. Dark matter needs to scatter on ions to have some sort of effect. And this is the scenario of dark matter millicharge. The dark matter has a very, very small electric charge and can communicate with ENM. Okay, and if you do this, then EDGES has a problem because the universe is mostly neutral at this point, very, very small amount of ionized particles. So now the cross-section that you need to explain EDGES, you need to be much, much higher. And so this is excluded, right, by the CMB. There was talk about how we could possibly evade the CMB constraints. Maybe the CMB constraints can be gotten rid of in some way, and then a high cross-section by edges would be perfectly fine. So is this a viable scenario from the CMB's perspective? And the answer is actually yes. So the CMB loses sensitivity to this interacting dark matter if it makes up a small enough portion of dark matter, right? So you assume that the rest is lambda CDM, and that just a very small portion, less than 0.4% of the dark matter, consists of this interacting component.
Is that interacting component, do you have a value for the can it be microcharge, or it doesn't depend on the charge?
Oh yeah, no, it depends on the charge. It depends on the charge. I don't have that slide in this, but if you're interested, I can show it.
But the other component would still heat up the hydrogen around the So that is, this one is kind of reducing the temperature. But if you have another component, that will probably again heat up the.
Oh yeah, so I'm assuming that the majority of the dark matter is just cold dark matter, just doing its thing that we usually assume dark matter does. It doesn't interact with anything. Is that what?
No, because usually the cold dark matter has a problem with the edges result because it is providing too much of temperature to the.
No, it's not removing enough temperature. The dark matter is heating.
Exactly.
So here she has some small fraction that absorbs a huge amount of heat.
Yeah, but
Yes.
that one is producing heat because it's interacting.
No.
Because annihilation cross section gets ruled out. But
There's no annihilation
No.
of this thing.
the cold piece would annihilate.
No.
No.
So the whole piece is performed without ionization?
So I'm assuming that the cold dark matter, the majority of dark matter doesn't communicate with the standard model at all.
Oh, so that's a kind of, it's a unknown, who
Yeah,
galaxy or?
exactly. So the rest of the dark matter is doing its own thing, not participating in this at all. And you're trying to see what millicharged dark matter can do, and this is what you need to do in order to have this be a viable, to even think of it as being a viable model. And the interesting thing about this is that it loses sensitivity because this small amount of dark matter that can be very strongly interacting with baryons essentially hides itself in the uncertainty of the baryon density. So it just looks like baryons to the Cmb. So this is why you lose sensitivity. And this is why there's a cutoff in the fraction, because you can't have too much of this because you can't have too many baryons. Okay. So this Cmb analysis was done in this paper, and we looked at specifically millicharged dark matter in the context of edges in other papers, and if people are interested in seeing that, I can show that afterwards. Okay, so this was the story of sort of looking for direct detection type events with cosmological observables.
Right, so these millicharges would interact with photons, right?
Mhm.
Because they do have.
That's right.
So wouldn't we have seen these stick out like a sore thumb and a lot of them?
Well, I mean, there's a region of parameters space that's going to be
Small enough
excluded.
charge that you would
Sure.
see.
Yeah, that's the Lipps analysis.
Just a tiny couple.
But you wouldn't see them produced copiously at the bar?
No, well, there are limits from, like Slack did a dedicated millicharge search, so that places a limit.
Below about 10 to the minus 4 electric charges, you can't make it.
The colliders have a limit of down 10 to the minus 2, like the, quarks, 3 quarks you're looking at, but our CDMS result goes down to 1/200 electron charge.
So, this is something that is definitely, that other experiments do comment on, and there's a region of parameter space that you can live in. Okay. Are there any more questions about this sort of dark matter scattering scenario? Because if not, then I'm going to switch gears a little bit. Huh?
You switch gears.
Okay, I'll switch gears and talk about tests that we can do in astrophysics, specifically in the context of gravitational waves. So I focused on a very, very specific type of dark matter. I'm assuming that it's a particle, that it's, we often think about it as being fermionic in a very specific mass range. So this is from a community paper that I worked on a couple years ago, this US Cosmic Visions. And we sort of outlined the different possibilities of dark matter models that could exist in the space of dark matter mass. Okay, so here's where I've been discussing something that's greater than a KeV, all the way up to maybe PeV masses, and this is sort of the broader. Let's kind of weaken the assumption about WIMPs and just extend this arrow to cover this entire region. But there are other possibilities that people have been thinking about. For instance, dark matter could be black holes. Dark matter could be these axion-like particles that are very, very light. And so a particular model here is called fuzzy dark matter, where it has such a small mass that its de Broglie wavelength is macroscopic. And so these particles, this fuzzy dark matter, can produce sinusoidal behavior, and the sinusoidal behavior can cause gravitational waves to form. Sorry, I contradicted myself there. I'm looking for gravitational waves. And in the black hole region, you can have dark matter, say maybe be primordial black holes. And so this idea has been looked at, and there are various regions of parameter space that you can live in and be a primordial black hole for dark matter. So the idea here is that, sure, we can look for these in sort of similar ways. We can do Cmb analyses. There's something to say about that. But the nice thing about these objects that create these very macroscopic classical objects is that we can look for gravitational wave signatures with them. Okay. And in terms of what type of gravitational waves I'm particularly interested in, so here's the spectrum in terms of frequency, and in terms of gravitational strain, this is just related to the amplitude that you expect to see of gravitational waves. And here we have your ground-based interferometers like LIGO, and they look for neutron-star mergers, intermediate mass black hole mergers. Future instruments like LISA will be space-based, and you can look at stellar mass compact binaries. You can look at supermassive black hole mergers. What I'm interested in is this region here at very low frequencies that's probed by, for instance, pulsar timing arrays. And this is where you can look at primordial gravitational waves. You can look at supermassive black holes. And this is the region in which things like maybe fuzzy dark matter could enter in and produce some effect. So what are pulsar timing arrays? Pulsars emit light at very, very regular intervals. So if you have any sort of gravitational wave that's produced between the pulsar and us, then the photon has to take a different geodesic, and you will see the timing of that very regular pulsar be altered very slightly, okay? And so this is the effect that you look for in, for instance, pulsar timing arrays. Interestingly, so this is taken from a pulsar timing array experiment. One of the things that hasn't been talked about as much is also using astrometry to do this. So if you have a star that you observe, and there's a gravitational wave passing through, then the star location can shift. The photon will look like it's coming from a slightly different place than where it actually is, and that shift over time, you can also search for gravitational waves in this way. So it overlaps a bit in frequency space with the pulsar timing, right? So we are not at the point, LIGO is the only ones that have seen gravitational waves. We're not at the point yet of pulsar timing arrays to have seen anything, but we will be soon. So what I'm interested in, instead of looking at various models that are supposed to give you these types of gravitational waves that could possibly be observed, I want to know how well can we even determine the information of the source of the gravitational wave from these experiments. So I really wanted to get into the nitty-gritty and ask what fundamental physics can we actually learn from this realistically. So this is work that I did with an undergraduate student at Johns Hopkins that I mentored, and we were considering a stochastic gravitational wave background. Now, astrophysically, we expect that all the gravitational waves in this frequency range will be dominated by supermassive black holes, binaries, spinning and producing these waves. So we have a bunch of them, right? Depending on the distribution of these supermassive black holes, we have a bunch of gravitational wave sources that have come in, and now we're seeing the overall effect. So this is the stochasticness of the gravity wave background. So what we can do is something very similar to what's done with the Cmb, right? We can look at a correlation function. So correlate the observable from the pulsar timing array in one location of the sky and correlate that with another location of the sky. And this is important because any tiny motion, any tiny thing that you haven't accounted for in systematic can present itself as a shift of the pulsar frequency, right? So you need some way to subtract out that background, subtract out systematics, and this is a good way to do it. Those systematics shouldn't be correlated with each other in the same way on the sky. So, for instance, this is this delta z is essentially the shift that I get, the frequency shift that I get, and we can look at two places in the sky and decompose this into multiples in a very similar way that we do with the Cmb. Now, interestingly, the community has not made their life very simple, mostly because we're used to plane wave expansions of things, of say gravitational wave sources or plane wave decompositions in physics in general. But this is not an ideal basis to use. We have a spherical sky and we observe on the spherical sky, so it kind of makes sense to decompose things in terms of essentially spherical harmonics. And so this has made life extremely simple. And so with this student, we were able to show that the overall calculation of the power spectra that are made could be simplified. The calculation could be simplified in a very drastic manner. So here, I don't want to go over all the details of what's happening here, but these F's are the information that is contained in the angular distribution. So this is all the angular information right here. And it's interesting because it's completely separated from all the frequency information of the gravitational wave. So in other words, this stochastic gravitational wave background, the signal, the amplitude of the signal will depend on frequencies and details of what actually made these gravitational waves, but their distribution across the sky does not. It's the same no matter what frequency you are at. So I also put these alphas here, and these alphas are looking at the different polarizations that you can have for your gravitational waves. So normally we just have our plus and cross polarizations. These are the transverse traceless parts of your gravitational wave. This is your massless graviton propagating, creating two polarizations, right, for spin 2 particle. But if there's any sort of, say, modification of gravity, or if there's any beyond GR scenario, then you can have other polarizations as well. So you can consider vector polarizations, and you can consider scalar polarizations as well. Okay, so these, when we observe this stochastic gravitational wave background, this provides a very easy test of GR, because all these different types of polarizations are going to give different angular dependencies across the sky, and we can directly do tests of GR in this way. Right. Okay, and so this total angular momentum formalism made life very easy, because so here are my power spectra that I expect, pattern on the sky, and I can essentially take this equation and write everything in terms of a table. And this is my calculation. This is all I had to do, and you will see if you expand in terms of plane waves, if you pick a bad basis, well, I guess I shouldn't say bad, it's a very traditional basis, expanding in plane waves. But it makes life so much more complicated, and you replace pages and pages of calculations with something that's very simple. And so this is, these are for PTAs, these are for astrometry, for your different polarizations. So you have scalar, you have vector, you have tensor polarizations. Okay. So this is the work that I'm continuing, essentially trying to characterize the gravitational wave background, and then building up and trying to say, can we eventually be able to distinguish gravitational wave sources? Can we say anything about fuzzy dark matter? Can we say anything about general relativity as tested here? Okay, so let me wrap up by just telling you about the future prospects in terms of these different research avenues that I've been taking recently. So the cosmic microwave background, we've come a long way since COVID, right? We have a lot of information from Planck. And the finer resolution, the more information we have, and the better that we can search for, non-standard dark matter type models. And there's a far future experiment that's been proposed called PICO, that's going to hope to be a satellite, the next generation satellite. There was a white paper recently that I was on about that. But we also have ground-based telescopes. Ground-based are limited because they don't get to see the full sky, but they do get to be bigger. And the bigger you are, the finer resolution you have. And so these experiments have undergone upgrades, and we hope to get new data from them soon. And what we have to look forward to in the next 5 years or so is the Simons Observatory. and eventually CMB stage 4 experiment. And so once again, there was a dark matter white paper with regards to dark matter physics that you could probe with cosmological observations from the CMB. In terms of galaxy surveys, I showed you the dwarfs that we've seen from the Sloan Digital Sky Survey, but we also have data from DES that I'm using now, and then eventually we'll have the Large Synoptic Survey Telescope, which will be a vast improvement. And once again, there are a lot of white papers. The Astro 2020 Decadal has produced a lot of white papers, so there's a lot of citations to these. So these galaxy surveys are definitely going forward. New ones will come online soon. In terms of cosmic dawn, there are radio telescopes that will go out and try to see if if the EDGES result, for instance, holds any water, and if it does, if there is that amount of absorption that I showed you earlier, then these telescopes should be able to see it fairly quickly. And so this is just taking the 21 centimeter line and mapping it on the sky rather than looking for this global signal, which is what EDGES did, this overall absorption. And then in the future, SKA is the telescope that is going to be very much looked forward to. It will be the biggest radio array that we built. And then in terms of the gravitational wave prospects, the pulsar timing arrays, recently there was an international pulsar timing array community, IPTA, that brought together 3 experiments across the globe, and they are utilizing or they're gathering their resources together to be able to look for gravitational waves through pulsar timing. And in the future, once again, the square kilometer array will also help with this endeavor of finding more pulsars. So I'll end there, and I just want to say that these cosmological observables, these astrophysical observables, provide a very, very interesting way to search for really fundamental physics. I focus mostly on dark matter physics here, but there are other fundamental questions as well, including tests of GR with gravitational waves. And so these various points in cosmological history will go and help us pin down the nature of dark matter as we get better and better data, as we have more data from different eras of our cosmological history. So, thank you.
Okay. Any questions?
Yeah.
What's the prospects of seeing the gravitational waves in the astrometry?
Oh, yes. I kind of glanced over astrometry because I was focused more on PTAs. So Gaia data will help a lot.
10 years of data, 5 years?
So not as much analysis has been done with Gaia, and projections have been done with Gaia, mostly because people have been focused on PTAs for this frequency range. So I don't know of any projections that have been done. Limits have been placed with current Gaia data and with other instruments as well, other observations as well. But I don't know at the end of Gaia's lifetime how much they expect to see. I don't think anyone's done that, to my knowledge.
How large is the astrometric shift?
Yeah.
Is it nanoparseconds or?
I know less about the astrometry than I do about the PTAs.
I think the idea is I get to correlate like lots of stars together, correlate small motions of lots of stars and go for correlating patterns.
Oh yes, it has to be a group effect.
Yeah.
You're definitely.
I think individually they're like some Gaia threshold.
Right.
Then the question is how low can you get global integration?
And even the PTAs, I was being very heuristic with, right? We don't see an individual pulse from the pulsar. We have to see a lot of pulses from the pulsar, and it's the accumulated effect that's able to constrain. But the pulsar, the PTAs are able to have like nanosecond precision in looking at millisecond pulsars. But I don't have the number for.
I mean, there's some suggestion that done with it, like what's called astrometric microlensing for Gaia, like black holes, so that the calculation is similar actually. So I forgot what the numbers are, but that was that's not an immediate I think, maybe.
Do you need like all the Ryan,
That's
like
a good
every
question.
single data point to observe for each star?
I imagine
analysis
that,
and all.
I don't think so in principle, but I imagine that would help.
For the Billy charge particle,
Yeah.
once you make the microcharge, does the 0.4% become higher fraction that's allowed, or
Oh, here, I can show you.
your CDMS style detectors will soon be able to look at microcharge?
Let me see if I have
So what's your constraint on these guys?
The last one we did was 1/200, but then you sharply lose because of thresholds. Just for the same reason as colliders are limited to small fractional charges.
So this is the region that I'm looking at. So this is epsilon, the fractional charge, dark matter mass. So here you're constrained by slack search. You have stellar and supernova cooling that come into play here, and these are the curves to get the right amount of absorption depth for edges at different fractions of dark matter. So here the CMB is kind of placing a constraint on the right-hand side, and as you go to lower mass, you need you need lower fractions. Of course, I have this shaded region over here called BBN. So BBN is going to have something to say about this, which is going to exclude a large portion of this parameter space. And so what I think is more important as a takeaway is not that, oh, no, I just can't possibly be, or, this scenario can't possibly be right because, of all these constraints and this is ridiculous. But I think it's more important to say that we need to be able to paint a consistent story cosmologically in terms of what we say that dark matter is. We need verification of the edges result in the first place, which will come from measurements of the 21 centimeter power spectrum. So even in the case that edges is not correct, or the interpretation of edges is not correct, it's still useful to know what to do for 21 centimeter cosmology, because we hope to be able to see it relatively soon.
You commented that this fraction on the right-hand end was basically equal to the error on the baryon density in the universe?
Yeah, it's not exact, but that's sort of where it's. That's
So I
where
guess
it's coming from.
the thing that's really doing this, if I imagine that Planck, for instance, had the most precise baryon measurement, then I would say, okay, I'm adding new things that are effective with baryons, so I'm decreasing the number of baryons until BBN is in conflict with that.
Yeah. So, so there's actually, the lithium abundance measurements have become really good actually in the past few years. And so the measurement of the baryon density from BBN is actually in slight tension with what Planck says. And so it was just a cute thing to point out that about, I think, 0.5% of the dark matter is small in terms of the dark matter, but is actually rather substantial amount of baryons. And so now you have two handles. You have something from BBN telling you something different from CMB at a 2 to 3 sigma level, and you're asking, is there something that the CMB is being fooled by that BBN wouldn't be? So
Does this bound actually improve that, or to move in this direction a bit is helping with you?
Yes, yeah. So you
So
can't have
if
too
you-
much, right? I think it's about 0.5% would get rid of the discrepancy entirely between the baryon density observed by Planck versus BBN.
Then what's telling us there's a bound at 0.4?
The CMB. Sorry, this is for the viability for the edges signal.
Right.
Right? So I'm saying that there essentially is no sensitivity that Planck has to anything below here, to any of this. So you're removing the you're removing the CMB constraining power, and saying, okay, now I am allowing something to happen that evades CMB constraints that can take effect at the time of cosmic dawn. Does that make sense?
But these relatively large milli charges, doesn't this thing really just act like baryons? At 10 to the minus 4? I mean, that's already super small, so probably not, right?
Yeah, so
It
it's.
is distinct from baryons in the Cmb signature.
So if you have too much of it and you are strongly coupling to baryons, you cause problems. Does that make sense? So if you have something that's like 0.05%, right? You can have a really high coupling in CMB, but you've created such a high coupling that you essentially have completely coupled the dark matter and the baryons together,
Right.
and now they're just acting like baryons.
Yeah, but that's perfect. That's what we want, to fix the baryon number anomaly with BBM.
Yeah.
Why
So
am I
I'm
allowed
saying,
to have that 0.5?
it's not that you're not allowed to have it, it's that you're not going to relieve the tension that much.
No, I mean the 0.5%.
Oh, the 0.5%, yes, yeah.
Yeah, what's the problem there?
Oh, 0.5% is that it's too much for the CMB,
In what sense?
in the sense that I can still see it and distinguish it.
From baryons?
Yes. Because it's too
Okay,
much,
'cause
right? Because you
Because
can
it's not
only.
coupled strongly enough to actually have cosmologically identical behavior to baryons. That's the point.
No, so you can't have too large of a baryon density or else you.
So I just decrease
alter-
the actual visible baryon density.
Yes, but, okay, sorry. Baryons undergo recombination,
Right.
and these don't.
So the universe
So-
is net charged? Or these just don't recombine because their binding energy is so low?
I assume that anything that's going to recombine is going to be the protons and the electrons. Because imagine if you had something that was, if you had a proton and you had a milli-charged dark matter particle, right?
Right,
That
but I have
charge
a really
is.
charged dark matter particle and a really charged anti-dark matter particle. Those two could recombine. But that would be with a much lower binding energy, right? That's,
Yeah.
So it wouldn't have happened yet?
Right, so it's going to be with a much lower binding unit, but the hydrogen is stable, right? The proton and the electron are going to annihilate.
No, but if you have milli charge, if they find
Yeah,
each
you can have
other,
a simple dark atom.
yeah, they'll just, it'd be like positronium.
The
They'll just-
positronium, but how stable is positronium?
Not very, that's the point, but you,
Yeah,
it would
exactly, so
annihilate
it's not going to
itself.
recombine.
But this could easily be a dark atom.
So now you will.
Yes, so absolutely, so there is, so I'm very interested in atomic dark matter for
Yeah.
other reasons as well. And so I'm looking at a very specific atomic dark matter model with particular people at MIT and at Johns Hopkins. And there we're considering if we have a dark electron, have a dark proton that aren't able to annihilate but form actual and undergo dark recombination, then yes. I don't assume that this happens with these.
Okay.
Yeah.
So for your stochastic gravitational wave diagram, so you said like you can distinguish the source, process.
No, that's the question.
Yeah, okay.
That's the question.
No, I was
Can you
wondering-
actually?
Yeah, so I was
Yeah.
wondering like a strong first order phase transition, that also produces gravitational wave around that field.
Ah,
So
yes,
can you
yes.
distinguish that from fuzzy dark matter or anything?
Can I
No,
distinguish?
can you like with this methodology?
Yeah, so you expect certain properties specifically about how things are distributed on the sky to be associated with one process versus the other. That's the hope, and that you would be able to distinguish these two things. It really depends on the number of pulsars we end up seeing. Right now, we have about 60 pulsars that are, and the more that you have, the more information you can extract, the better you do. So there's a signal to noise question that has to be answered as well. So this is why I don't want to like just jump into the particular models and be able to say, yes, with SKA we're going to be able to do this, because we actually need to know how much is coming from astrophysical, how much is coming from possible new dark matter models, and can we disentangle that in the first place, rather than just setting bounds. So this is one of the things that I'm interested in with the gravitational waves.
Okay, well,